Hello, this is the lecture for exponential equations. All right, there's a couple methods for solving exponential equations. The easiest method is to establish like bases, right? So if you have an equation like these here, if you can write the equation so that the same base is on both sides of the equation, then we can use the one-to-one property and know that the exponents are equal. So in this first example, we have 4 to the x equals 6. If I could rewrite 16 as an exponential expression with base 4, and I can because 16 is 4 squared, then I can say that 4 to the x equals 4 squared. Since the bases are the same, the exponents have to be the same. And I can then say that x equals 2. Okay, and similarly over here, if I could rewrite 243 as an exponential expression with a base 3, then I would know what that exponent needs to be. Let's see, I think 3 to the 5th is 243. Let's check. Oops. Yeah, it is. So if I rewrite 243 as 3 to the 5th, 3 to the x then equals 3 to the 5th, and by the one-to-one property, since the bases are the same, the exponents have to be the same. So x equals 5. Okay, look at this one here. 25 to the x equals 5. Well, let's see. I think I can write 25 as an exponential expression with base 5. 25 is 5 squared. So I could write this as 5 squared to the x power is equal to 5. And of course, there isn't an exponent there, but it's like there's an invisible 1, right? And that's like 5 to the first power, right? And when we raise an exponent to an exponent, or when we raise a power to a power, we multiply. So then we have 5 to the 2x power equals 5 to the first power. Now I can use my one-to-one property, and I can say that 2x equals 1. So then dividing both sides by 2 shows us that x equals 1/2. All right, one more. Oh my, 1/3 to the x power equals 9. Okay. Well, what common base should I try to rewrite these two sides in? Well, I know that 9 is 3 squared. So if I could write 1/3 as an exponential expression with a base of 3, I'd be good, right? Well, I can do that. See, 9 is 3 squared. 1/3 is the same as 3 to the negative first power, right? Raised to the x power. So then 3 to the negative 1x, or 3 to the x, equals 3 squared. So then negative x equals 2. If I multiply both sides by -1, x has to be -2. Okay, so that's one method to solve exponential equations. Simple ones like this, if I can establish the like bases on each side, then that works for me. I can use the one-to-one property and know the exponents are the same. That method, however, doesn't always work, right? It doesn't always work. So another method that's extremely helpful is to convert the exponential expression over to logarithmic form. All right, here in this example here, 3 to the 2x equals 80. I can't think of the same base that I could write 80 as an exponential expression and then 3 to the 2x. In fact, it'd have to be base 3. I could do 3 to the 4th, but that's not 80, that's 81. So I can't do that. So I'm going to use this second method of converting this exponential equation into a logarithmic equation, right? So let's see, when I rewrite 3 to the 2x equals 80 as a logarithm, it's going to be log base 3 of 80 is equal to 2x, right? Well, what is the log base 3 of 80? Well, I don't know. I don't know what power to raise 3 to get 80. it's almost 4, but not quite. So let me use that change of base formula. Let me use that change of base formula and rewrite log base 3 of 80 as the common log of 80 over the common log of 3. That's still equal to 2x. All right. And then, of course, x, if I divide both sides by 2, right, then I see that x is going to be equal to the common log of 80 over the common log of 3, or I could have used natural log as well, right? And then all of that gets divided by 2. Well, that's an exact answer, but it's in a very ugly form, isn't it? It's in an ugly form. So I need to convert that fraction, compound fraction. I need to convert that a little bit, right? That's log 80 divided by log 3 over 2 divided by 2 over 1. So when I simplify, this becomes the common log of 80 over 2 times the common log of 3. And if I want to approximate that, I can stick that in my calculator. Either way, right? All right, let's see what that is. Common log of 80 divided by 2 times the common log of 3. And my answer is 1.9943, approximately. Okay. Look at the second example over here. Well, can I write 31 with a base 4? No. And I have a problem here. I have a little bit of a problem here. Look, there's a number out front. There's a coefficient, if you will, right? Or a product out there. I can't convert with that. So what do I do? What do I do with it? I can't bring it up to the exponent because this is not a logarithm. This is an exponential expression. But what I can do is divide both sides by 7 to get rid of it on that left-hand side, right? Then I have 4 to the x power equals 31 over 7. I can convert that to log form and continue solving, right? So log base 4 of 31 divided by 7 is equal to x. All right, there's an exact answer. Now, if I want to approximate that, I can use my change of base formula. Let's use natural log this time instead of common log because it doesn't matter. We'll get the same answer. So the natural log then of the argument here is 31 over 7 divided by the natural log of 4. There's an exact answer. I can approximate that. Use the calculator to approximate it. We use 4 decimals. Let's see. The natural log of 31 divided by 7. All right, and we'll divide that by the natural log of 4. And it approximates to 1.0734. When I use 4 decimals. All right. So if we can establish like bases, that's one way to solve an exponential equation. If we can't, then we just convert it over to logarithmic form and solve it that way. So 2 methods here for solving exponential equations. Now, one thing to note, if you have a base e, you always want to use natural log. That's going to make it easier instead of common log. But you don't even really have to think about it. If I were to look at this and say, well, I can't establish the same base because the base is an irrational number. So let me just convert that over to logarithmic form. When I do that, log base e of 12 is equal to 1 minus 3x. Well, log base e is natural log, right? So this is the natural log of 12 equal to 1 minus 3x. Now I just want to solve for x. Well, we'll subtract that 1 from both sides. So then the natural log of 12 minus 1 is equal to negative 3x, and then divide both sides by the negative 3. So my exact answer for x, I'll do it up here. My exact answer for x is going to be the natural log of 12 minus 1 over negative 3. And if I want to approximate that in the calculator, let's see, natural log of 12 minus 1, press enter, and then divide it by negative 3. My answer is going to be approximately negative 0.0 4950 if I'm doing 4 decimals. Okay. All right. Let's do one more example here. Look at this guy. It's an exponential equation, but look at this. I've got a variable in the exponent on both sides. That's different than anything we've seen, isn't it? Well, we've only talked about establishing the same base, like bases, which we can't do between 3 and 5, or converting to log form, and I could do that, but it's going to be kind of messy, right? Well, there's a third method. There's a third method for solving exponential equations, and that third method, I might say, is take the log of both sides. Right? This is just using this one-to-one property in reverse. Right? If I take, I can do that. I can take the log of both sides. So I could rewrite this exponential equation as, I think we'll use natural log here instead of common log. It doesn't matter. I could have used common log, but I think I'll say the natural log of 3 raised to 2x plus 1 is equal to the natural log of 5 raised to the 3x minus 4. Okay, so that's just kind of my one-to-one property. And if I had the natural log of something equal the natural log of something else, I would know that something equals to something else. So I can take the log of both sides here. I can use that in reverse. Now that these are logarithms, what do you think we're going to do here? We can bring down that exponent, right? We can use the power rule for logarithms, or the power, and we can bring down that exponent. So let's do that. So then we have 2x plus 1 times the natural log of 3 is equal to 3x minus 4 times the natural log of 5. All right, now what? Well, I've got parentheses here, so I think I'm going to go ahead and simplify. Let's distribute this natural log of 3 to both terms and the natural log of 5 to both terms. All right, so then I'll have 2x times the natural log of 3 plus 1 times the natural log of 3 is equal to 3x times the natural log of 5 minus 4 times the natural log of 5. Okay, now what am I going to do here? Well, I'm solving for x, right? I'm solving for x. So let's see, there's an x, and there's an x. I think I need to get those terms with the x in them on the same side of the equation, right? So let's subtract that 3x times the natural log of 5 from both sides. And this one doesn't have an x, it's natural log 3. So let's move that to the right. We'll subtract a natural log of 3 from both sides as well. Okay, and what do I have left then? Let's see, these guys add out. On the left-hand side, like I said, 2x natural log of 3 minus 3x natural log of 5. Well, those are not like terms, right? This natural log 3 natural log 5 is different, so I can't combine them, so I'll just write it. I'll say it's 2x times the natural log of 3 minus 3x times the natural log of 5, and that's going to be equal to what? What do I have over here? Can't combine those. Those are not like terms as they are right now either. So that's going to be equal to negative 4 times the natural log of 5 minus the natural log of 3. All right, so I've got both terms with the x on the left. Now how do I proceed to solve? I can't combine them. They're not like terms. I mean, I could approximate. I could put that in the calculator, 2 and 3, and approximate a decimal, but I don't want to do that. I want an exact answer. So you know what I'm going to do? I'm going to factor out an x. There's one here, there's one here. So let's factor that x out. When I factor that x out, and we'll do it over here. I get x times 2 times the natural log of 3 minus 3 times the natural log of 5, which of course is still equal to negative 4 times the natural log of 5 minus the natural log of 3. All right, now you see what we need to do? We just need to divide both sides. We just need to divide both sides by this 2 natural log of 3 minus 3 natural log of 5. Okay, and when I do that, they'll divide out on the left-hand side. That's an ln. And here, let me rewrite it so we can see it better. So here's what I'm left with. X then is equal to, here's our exact answer, negative 4 times the natural log of 5 minus the natural log of 3 divided by 2 times the natural log of 3 minus 3 times the natural log of 5. There's my exact answer. Let's put that in the calculator and approximate that to 4 decimals. Let's see. My numerator, negative 4 times the natural log of 5 minus the natural log of 3. There's my numerator. It's negative 7.536 and some more. That's going to be divided by, and I better use parentheses here because this calculator is not too smart. It's going to be divided by 2 times the natural log of 3 minus 3 times the natural log of 5. What do I end up with? My approximate answer is 2.8644. Okay. Oof, that was a good problem, wasn't it? Lots of work there. All right. So let's end the lecture by taking a look at applying exponential equations or applications that involve exponential models. Okay, recall from previous lectures, right? We have a formula that we can use, an exponential formula that works for, to find future value of money when compound interest is involved. And that formula is like this. Some future value, some future amount is equal to the principal amount, or the current value, times 1 plus the interest rate divided by the compound period raised to the compounding period times the number of years that investment is in place, right? So that's that formula. Let's see what we want to answer here. How long will it take $10,000 invested at 3% compounded annually to earn $2,000 in interest? All right, there's my formula. Let's see what values we've been given here. How long? Well, that's the t, right? So I don't know what the t is. That's what I'm looking for. How long? How many years? Will it take $10,000 invested? Sounds like my principal amount here, my initial amount, the amount that I'm starting with is the $10,000. That's what I'm investing, right? We're investing at 3%, so that's my interest rate. That'll be 0.03. The compounding is annually, so I'm only compounding 1 time per year, so n is going to be 1. And it's earning $2,000 in interest. Well, if it's earning $2,000 in interest, the future value of my money, or my A, it's going to be the $10,000 that I originally had, plus the $2,000 interest that was earned, or $12,000. All right, so let's plug in the values that we know and see if we can solve for t, for how long, for the number of years. All right, so the A we said was 12,000. So then 12,000 is going to equal the P, that was 10,000, times 1 plus the interest rate, that's 0.03, divided by the N, compounding period, it's only once per year, so 0.03 divided by 1, raised to the NT power, that's going to be 1 times T. All right, let's simplify a little bit. Let's see, 12,000 is equal to 10,000 times 1 plus 0.03 divided by 1, that's just 1.03, right? Raised to the 1t power, that's just to the t power. All right, there's an exponential equation for us to solve. Well, I got this coefficient, right, or product here in front of my exponential expression, and I can't have that if I want to convert this over to logarithmic form, right? That's probably the method that I would use here. So I'm going to need to divide it away. Let's divide both sides by 10,000. So then 1.2 is equal to 1.03 to the t power. Right. Now I can go ahead and convert this over to logarithmic form, or I could take the log of both sides. That would work. That method works as well. I think I'm going to convert it, though. I think I'm going to convert it. So let's see. When I convert this, we get log with a base of 1.03 of 1.2, that's my argument, is equal to the t. Okay, so there's an exact value. If I wanted to approximate that, well, I think I'm going to have to use that change of base formula, right? Because a base of 1.03 is not easily found in my calculator. So let's use that change of base formula, and we'll use common log this time. So t then is going to be equal to the common log of the argument, 1.2, divided by the common log of the base, that's 1.03. There's our exact answer. Our approximate answer, I don't know about you, but that doesn't mean how much to me. I want to know how many years. So let's approximate it. Common log of 1.2 divided by divided by the common log of 1.03. And the answer is 6.1681 years. Okay? Let's look at another application. So sometimes, okay, so here's an application that's involving population, right? They're giving us the model this time. They're saying that the population of India was about 1.25 billion in the year 2013. The annual growth rate was 1.2%. So we could build this model knowing that, but they've given it to us. The model then for the population at some future time is going to be 1.25 times 1.012 raised to the t power, right? Because just like with the compound interest model, the general form for an exponential model, when we know a percentage growth rate or a percentage decay rate, the generic model is going to look like this. Some function is going to equal the initial value, whatever the initial value is, maybe we call it p sub 0, times 1 plus the growth rate, or 1 minus the decay rate raised to the t power. Right? So that's our model that we have here. T is going to be the number of years since 2013. Right? To the nearest thousandth, what will the population of India be in the year 2031? All right, well, I need to know how many years after 2013 2031 is, right? Because that's what T represents. So let's find that out. 2031 minus 2013 is 18. All right, so 18 is my T. Now all I need to do is plug that in and evaluate my model. I'm looking for P of 18, right? So that's going to be 1.25 times 1.012 to the 18th power. All right, let's put that in a calculator and see what it is. 0.25 times 1.012 raised to the 18th power, and it's 1.5494. 1.5494, and we're in context here, so what are our units? 1.5494 million. These are millions, right? Billions. Nope, sorry, billion. 1.5494 billion people. All right. So many exponential models take this form, the form very similar to the form, really it's the form that the compound interest formula uses, where it's some initial value. P sub 0 is our initial value, or our initial amount. Sometimes you'll see that. Sometimes you'll see that as A sub 0, times 1 plus the interest rate raised, or plus the growth rate raised to the number of units of time, right, that our model uses. Here we were using years for unit of time, and our growth was 1.2%. Of course, if we have a decay rate, this R is going to be something negative. But not sometimes when we use continuous growth, though. Do you remember we had that model that PERT model with continuous growth. When we use continuous growth, there's a little bit different form we might see. So instead of the future value here, we're calling, so instead of P of t equals the initial amount times 1 plus the growth rate raised to the number of years or number of units of time, right, to the t power, we sometimes see this continuous growth rate formula. It says some future amount is going to be the initial amount times E, Euler's number, the number E, raised to the RT power, where R is the growth rate or decay rate relative to the population, and T is the units of time. All right, let's look at an example using this alternative form with continuous growth. Many scientific applications use continuous growth. Many financial applications do not. Here we have a situation where the number of bacteria in a culture is given by the function n of t equals 1,000 e raised to the 0.1 t power, where t is measured in hours. All right, in hours. So the first question is, what is the relative growth rate of this bacterium population? They want us to write it as a percent. Well, the relative growth rate is our R, right? R is our relative growth rate, and our R here is 0.1, all right? 0.1 is going to be 10%. So we'd say 0.1, sorry, I didn't do that. 0.1, which is 10% written as a percent. All right. What is the initial population of the culture? Okay, so let's see. We'll do color coding here. That was our initial growth rate. What is the initial population? The initial population, that's this p sub 0 here, right, in the formula. It's the coefficient in front of the e. You can think about it that way. So here it is. It's 1,000. So my initial population, when we start out here, when t is 0, is 1,000. Okay, so if I know the form, I can see it from the pattern that the initial population is 1,000, but I could also have evaluated that, right? Look, I could have said n of 0 is equal to 1,000 times e raised to the 0.1 times t equals 0 times 0 power, right? Well, 0 times 0.1 is just 0. E to the 0 power, of course, is just 1. So it'd be 1,000 times 1. All right, the last question here, how many bacteria will that culture contain at time at t equal 5 hours? 5 hours. After 5 hours, we're going to find n of 5. We'll just plug 5 in for t. All right, so that's going to be 1,000 e to the 0.1 times 5. All right, and our calculator will tell us what that is. 1,000, I think I'll use my e to the x key. There it is. And my exponent is going to be 0.1 times 5, or 0.5. So that's my answer, 1,648. Now, do I want a decimal here? I do not. I don't, because I can't have a portion of a bacteria, can I? So I don't want to round up either, because I don't quite have that next bacteria. All I have is 1,648 and then 7/10 of another bacteria. So I want to make sure that I truncate. Okay. Let's see. So they're just 4 examples. Let's look at this one here. Here we have a function d that takes t as its input. Okay, so d of t equals 600 e to the negative 0.00259 t. And this function is used to find the number of milligrams, that's going to be d, of a drug that's in a patient's bloodstream t hours after it's administered. All right, how long? Here's an interesting question. How long until half of the quantity remains? half of the quantity remains. Well, remember our standard form here, our general form, d of t, it's going to equal the initial amount. Oh, we're calling that p of 0, weren't we? That initial amount times e to the RT. Okay, well, the initial amount, if we look at the pattern here, the initial amount is 600. Yeah, I could calculate it also by putting 0 in for t, but I don't need to do that because it's always going to be the coefficient in front of the e. All right, so there's my initial amount. I want to find out how long until half that initial amount is there. Well, half is going to be 600 divided by 2, or 300 milligrams. All right, so that's the future amount that I'm interested in. So that's going to be the d of t. So let me set this up. Let me set up this equation and see if I can solve. So 300 then is going to equal the initial amount, the 600 times e to the negative 0.00259 t, and I just need to solve for t. All right, I've got this coefficient I need to get rid of, right? So let's divide both sides by 600. So then 0.5 is equal to e to the negative 0.00259 t. All right, and I think we'll just go ahead and convert that. I could take the log of both sides, that works as well. But I think I'm just going to go ahead and convert that to log form because I know it's this base e. I'm not going to have to use the change of base formula. That's going to be a natural log, right? So when I convert that to a logarithmic equation, I have log base e of 0.5 is equal to negative 0.00259 t. Right? Now, of course, log base e is natural log, right? It's all right. Natural log of 0.5 is equal to that negative 0.00259 t. And then to solve for t, I just need to divide both sides by that negative 0.00259. Okay, so there's my exact answer. Let's put in the calculator though, because that doesn't tell me anything about how long this is. Let's see what that approximate answer is. All right, natural log of 0.5 divided by negative 0.00259, and it's 267.62. 267.62. Well, there's some more that I could put there. 44. We'll go ahead and put them. So what are we measuring? What is our t here in? It's hours. So that's 267.6244 hours after the drug was administered. All right. Let's look at one more application. All right, here's one. Here's an exponential decay. The half-life, whenever you see half-life, that's going to be exponential decay, right? That's going to have a negative exponent, or it's going to have a negative decay rate. So the half-life of radium-226 is 1,590 years. If a sample contains 100 milligrams, how many milligrams will remain after 4,000 years? All right. We're starting with 100 milligrams. Well, what is the standard form for the model? Let's put that up here so we've got that to look at. Let's see, our future amount, or we'll say, should we call it P? I don't know, I guess. So P of T is going to be the initial amount, or P of 0, right, times, and since I don't have a growth rate or anything here, I'm going to use E, right? I'm going to say it's continuous growth, or decay in this case, continuous. So P sub 0 times E raised to the RT power. So what are they telling me here? I know a few things. I know the half-life is 1,590 years. Okay, that sounds like a T to me, right? I think that's going to be my T. The sample contains 100 milligrams. Well, that's what we're starting with, right? So that sounds like my P of 0. I want to know how many are there after 4,000 years. That sounds like a T as well. It's a number of years. right? That's the number of years. What don't I know here now? I've got two t's, I've got an initial amount. Can I find my half-life, my half amount? Well, yeah, my p of t, that's going to be half of what 100 is, right? After half-life, I'm going to have 50 because that's half of 100. Well, I don't know the rate here at all, though. I have 2 times. Where do I go with this? Where do I go with this? Well, let's just forget about this first part. Let's see if we can build our model first. Let's see if we can build our model and try to find out what that decay rate is. Let's see if we can find that decay rate. All right, I think I can build my model because I know the initial amount and I know the future amount because it's a half-life. That means that's when half-life means when half of the quantity remains. So I can do this. I can say 50 equals 100. That's my p of 0. P of t is 50. 100 e to the r. And I know how long, since the half-life is 1590, I know how long it takes this 100 milligrams to decay to 50 milligrams. It's going to be 1590. Okay, now I have this equation. I can solve for that rate. I can solve for that relative decay rate, of the decay rate of radium-226. Let's see, I'm going to need to lose my coefficient, so let's divide both sides by 100, right? So then 0.5 is equal to E to the 1590 times R. All right, let's convert that to exponential form. Log base E of 0.5 equals 1590R. Log base E, of course, is natural log, right? And I want to divide both sides by that 1590, right? So for R. So R then is going to be the natural log of 0.5 divided by 1590. Let's approximate that. Let's see if we can get a decimal. Let's approximate that. Natural log of 0.5 divided by 1590. Ooh, look at that small number, right? Look at that small number. Now I could write that out, or I could leave the exact, I could use the exact expression for the exact value. Let's see what that number is. All right, -4, so it's going to be negative, e to the negative 4, so it's going to be 0.0004359. I'll use four significant digits there. That is a very small number, isn't it? All right. Well, I know what my R is now. That's my R. Now I have a model that I can write. Okay, what is my model looking like here? There's my model. The amount in the future is equal to the initial amount, which is 100, times E to the, and here's my R. My R is negative 0.000439 T. There's my model. I can now use my model to find P of 4,000, right? P of 4,000, or the amount of radium that's left after 4,000 years, it's going to be 100 times E to the negative 0.000439 times T, that's going to be 4,000. Right, let's use our calculator and see what that amount is. So 100 times E, let's use E to the X key, times E to the negative 0.000439 times 4,000. And it looks like I'm going to have 17.4890 or 489. I've been using 4 decimals, so I just will 17.4890. What are our units here? Milligrams of radium-226. Now, does it make sense? Well, the half-life was only 1,590 years. That would give us 50 milligrams, right? So after 4,000 years, I should have quite a bit less. So it does make sense to me that 17.4890 is our correct answer. All right, this ends the lecture on exponential equations.